Let's talk a little bit about multivariate variances and covariances. So we're going to define for a random vector x, the variance of the random vector x, which say is n by 1, is going to be the expected value of the outer product of x minus mu with itself. So where here mu is equal to the expected value, it's the vector expected value of x. So this quantity here has the property that, for example, the diagonal element, or the first diagonal element, is expected value of x1 minus mu1 squared. Okay, so it's just the ordinary variance of the first element of the vector. The second diagonal entry of this matrix is just the expected value of x2 minus mu2 squared. The first off-diagonal element of this matrix, in either above the diagonal or below the diagonal, is just the expected value of x1 minus mu1 times the expected value of x2 minus mu2. And that is exactly the covariance between x1 and x2. So the ijth element of this matrix is the covariance between the I element of the vector x and the j element of the vector x. So this quantity is called the variance covariance matrix. And just like the variance calculation for univariate random variables has a shortcut formula, the variance calculation for multivariate random variables also has a shortcut calculation. So the variance of x is expected value of x minus mu transpose. So let's use our rules. So that's the expected value of x transpose minus x mu transpose minus mu x transpose plus mu transpose. So that's equal to the expected value of x transpose. Then this quantity, mu, is not random, so we can pull it out of the expected value. And the expected value is a linear operator, so it moves across these sums. Okay, so we can write this as the expected value of x times mu transpose minus mu times the expected value of x transpose, and the mu transpose has nothing random in it, so that's mu transpose. But this is just mu transpose, because remember, mu is defined as expected value of x, and this is just mu transpose again, so we get minus mu transpose minus mu transpose plus mu transpose. So we get that the shortcut formula is the expected value of the outer product of the x's minus the outer product of the expected value of the x's. Okay, so that's a simple shortcut formula. The variance has nice properties, not unlike the mean. It would be nice if the variance was a linear operator, but it's not. So we cannot say, for example, that variance of x plus y is equal to the variance of x plus the variance of y. So we cannot say that unless the vectors x and y are mutually independent, or uncorrelated at least. So what we can say is that, first of all, that the shifts in the variance shifts have no effect on the variance. So if we take the variance x and shift it by a constant vector b, that's just the variance of x again. Just like in univariate cases, of course, the distribution of a random variable, if it looks like this, it's going to have the same variance if we shift it over by a little bit. So the variance doesn't change if we shift. And then another important property is the variance of a times x. If we have a variable that we'd like to pull out of a variance, that is equal to a variance of x, a transpose. So when we pull a matrix or vector out of a variance, it sandwiches the variance, and so you get sort of a is the bread, and then the variance of x part is the meat. So it sort of sandwiches the variance, and when you pull it out, it has to go in both directions with a and a transpose. Look back at the definition one more time. I also want to point out that the variance covariance matrix is clearly symmetric. If you were to take, for example, the transpose of this matrix, remember that transposes move into expected values, you'll find that you get the expected value of the same exact thing. So it is symmetric, which is a good thing, because we know that, for example, the ij off diagonal covariance xi and xj is equal to the covariance of xj and xi. The bivariate covariance operator is exchangeable with this argument, so it has to be symmetric. So it's nice that we can see that property very directly. So those are some of the key things to know about multivariate variances or variance of vectors, and we'll use these facts a lot throughout the class. So it'd be nice to commit, especially this formula right here about pulling a matrix out of a variance calculation. That's quite useful.